Welcome to this presentation for the March meeting 2020 about the evaluation of the performance of a 7-qubit surface code. My name is Remm, and if you have not yet seen the first part of this presentation by Christian Andersen about the performance of the individual elements of our device, make sure you do so. We start off by looking at the gate sequence that we need to run to operate our surface code. We start with all the qubits in the ground state, and we then initialize the data qubits with single qubit gates depending on which logical state we want to prepare. We then start with an XXXX stabilizer, which we implement by mapping the X parity of the data qubits to the ancilla A2 by single qubit gates and 4 2-qubit gates. We then measure out the state of the ancilla to extract the stabilizer outcome. As we are reading out the ancilla A2, we map the two ZZ stabilizers to the ancillas A1 and A3. By doing the stabilizer measurement sequentially instead of simultaneously, we avoid frequency collisions during simultaneous 2-qubit gates. We can repeat these stabilizer measurements for n rounds, with one full round taking on our device about 1.9 microseconds. After running the stabilizer measurements for n cycles, we read out the data qubits either in all Pauli bases for state tomography or just in the Z or X basis to read out the logical Z or X operator. Next, let's see how well we can prepare logical states using our scheme. To prepare the logical zero state, we start out with all the qubits in the ground state. Next, we run one full round of stabilizer measurements. If both the stabilizer outcomes were +1, then in the ideal case, we project our initial state to the logical zero state, which is the 4-qubit GHZ state. We characterize the 4-qubit state by state tomography and extract the following density matrix. As you can see, the main deviation from the ideal state, shown in wireframes, is the slightly reduced amplitude of the real part of the density matrix, amounting to a fidelity of 70.3%. We can divide our 4-qubit state into two parts. There is the part where 4 qubits are within the logical subspace, denoted rho L, and then there is the part where an error has occurred and the qubits are not in the logical subspace. We are within the logical subspace with probability of about 72%. By projecting the 4-qubit density matrix to the logical subspace, we recover the following density matrix for the logical qubit. It has fidelity of about 98% to the target zero state. We repeat the same procedure for the logical plus, minus, and 1 state, and in all cases we achieve a fidelity of our logical state above 94%. It's important to emphasize at this point that the state preparation is probabilistic in the sense that we only look at the data if the stabilizer outcomes are all +1. Next, we will look at how the logical operators evolve if we repeat our stabilizer measurement for n cycles. To read out the logical Z operator after repeating the stabilizer measurements, we read out the data qubits in the Z basis to calculate the logical Z operator, which is the product of the two measurement outcomes. We only analyze the data where all the syndrome outcomes were +1, and in addition, we check that the Z stabilizer values are also +1 for the classical measurement outcomes to check for any errors that happened after the last stabilizer measurements. You can see the logical Z operator for the logical 0 and 1 state after n cycles in this plot. We measured this for up to 10 cycles, which corresponds to 20 microseconds. As you can see, the logical Z operator decays very little over this time. By fitting the data to an exponentially decaying model, we extract the logical lifetime of our qubit, which is around 60 microseconds. It's worth noting that this is much better than the best physical lifetime of our qubits, which is 17 microseconds, shown in the dashed lines on the same plot. Because the physical qubit decays towards the zero state, but the logical qubit towards the mixed state, the axis for the physical qubit is modified. We also did a master equation simulation taking into account the physical qubit decay, decoherence, and readout errors, and also the residual ZZ couplings between the neighboring qubits. And the results are shown in the solid lines. As you can see, the simulation matches our data quite well. This tells us that the main limitation of our algorithm is qubit decay and decoherence. We can do a similar analysis for the logical plus and minus states by reading out the qubits in the X basis and doing a classical check for the XXXX stabilizer. We extract the logical coherence time of 72 microseconds. And again, the master equation simulation fits the data quite well. Because we only look at the data where all the syndrome measurement outcomes were +1, at each round we have less and less data. After 10 rounds, only about 0.01% of the data remains. This is also the reason why we did not look at larger number of cycles. We can look at the distribution of the stabilizer outcomes at round n, condition that no errors had been detected in prior rounds. We see that the probability of detecting no errors is around 50%, whereas the probability of detecting multiple simultaneous errors decays exponentially with the number of errors detected. So to summarize our results, we have demonstrated a repeated quantum error detection on our 7-qubit device. And the lifetime and coherence time of our logical qubit is significantly better than any physical qubit on our device. The main limitation of our device, causing a small success probability after many rounds of error detection and also causing the reduction of logical lifetime, is physical qubit decoherence and decay, as shown by master equation simulations. As the next steps, we want to move from the 7-qubit distance 2 surface code, which allows only for quantum error detection, to a 17-qubit distance 3 surface code, allowing also for quantum error correction. But to go below the quantum error correction threshold, we need to improve the physical qubit coherence times to allow for higher fidelity gates.